Good morning, everyone. I am Mayank Parab, and this is my team, Vansh Marate and Anirudh Nurani. We are presenting a project titled Adaptive ECG Biometric System. The main idea behind the project is to use the electrical signals of the human heart, known as the ECG, as a unique and secure biometric for authentication. Traditional biometrics, such as fingerprints, facial recognition, or iris scans, are commonly used but have major drawbacks. They can be copied, forged, or spoofed using photos or molds. ECG authentication solves this problem because it is a living biometric which can only be generated by a real beating heart. This makes it much harder to fake and automatically ensures liveness detection, offering higher security. Another advantage is continuous authentication, meaning ECG signals can be monitored in real time to constantly verify if the right person is still present. In short, ECG biometrics combine security, adaptability, and continuous verification in one system. Before discussing how our system works, let's briefly understand the ECG signal itself. The ECG waveform consists of three main parts. The P waveform shows atrial depolarization, a small and slow signal. The QRS complex is sharp and high frequency, representing the main ventricular contraction. The T wave represents ventricular recovery or repolarization. Each individual's ECG has a unique shape and timing, making it an ideal biometric feature. The useful frequency range of ECG is between 0.05 and 150 Hz, and in our simulation, we use a sampling rate of 500 Hz to capture all signal details accurately.
There are four main stages: signal acquisition, preprocessing, feature extraction, and authentication. First up, signal acquisition. In real world implementation, ECG signals would be captured from the body using electrodes and an AT8232 sensor. Since we are not using any hardware yet, we simulate the ECG signal in MATLAB using mathematical functions that resemble real heartbeat patterns. Second up is pre-processing. The simulated ECG is mixed with various noises such as baseline drift, power line interference, and random disturbances. We then use two filters for it: a Butterworth filter to remove high frequency noise, and an adaptive LMS filter that automatically adapts to minimize correlated noise while preserving the ECG's true waveform. Third up is feature extraction. Once the signal is clean, MATLAB detects R peaks, the sharp spikes of each heartbeat, and calculates the RR interval between them, which represents the time difference between consecutive peaks. We also calculate the spectral energy in the range of 5 to 15 Hz corresponding to the QRS region. These two parameters, the mean RR interval and spectral energy, form our feature vector. Last up is the most important part: authentication. The extracted feature vector is compared with a stored user template. If the difference between them, measured as Euclidean distance, is below a certain threshold, the system prints user authenticated successfully. Otherwise, it prints authentication failed. The simulation shows different stages: the noisy ECG, the filtered waveform, and the final clean signal with detected peaks. Since we are currently simulating, MATLAB serves as a testing and validation environment before moving to actual hardware implementation.
So here is the MATLAB code for our project. We divided our MATLAB program into 6 main steps, each representing a functional stage of our simulation. The first is ECG signal simulation. We generate a synthetic ECG waveform using a sawtooth function to represent the heartbeat pattern. Small sinusoidal components are added for P and T waves, and different noises like baseline drift and power line interference are added to simulate real world conditions. The second step is Butterworth filtering. A fourth order Butterworth low pass filter is applied to remove unwanted high frequency components and smoothen the signal. The third step is adaptive LMS filtering. The least mean square adaptive filter further refines the ECG signal by minimizing correlated noise and continuously adjusting filter coefficients for better accuracy. The fourth part is feature extraction. MATLAB detects R peaks in the filtered signal and calculates the mean RR interval. Then, using FFT, it computes the spectral power between 5 to 15 Hz. Together, these two values form our feature vector. The fifth part is template matching. The system compares the current feature vector with a stored template. If both match closely, meaning the distance between them is below a certain threshold, The user is authenticated successfully. The last part is plotting the results. Finally, MATLAB displays four plots: the noisy ECG, the filtered output after Butterworth and LMS filtering, R peaks, and a bar chart showing the extracted features. These six steps together demonstrate the full working of our adaptive ECG biometric system from signal creation to authentication. So, when I run this code, since the this is currently set to not match with the template, we observe that in the output it shows authentication failed. However, when we change it so that it matches, uh, you will see that it says authentication successful. It says user authenticated successfully. So that's it for the code. Now, if we were to implement this system in hardware, we would require an AD8232 ECG module to capture the heart's analog signal. ECG electrodes attached to the body, typically the left, right, arms and legs. A microcontroller such as an Arduino Uno or ESP32 to sample the signal at around 250 to 500 Hz and send it to MATLAB or another processor for analysis. The same filtering and feature extraction algorithms used in MATLAB can be applied to this live data for real-time authentication. Now, coming to the applications, this system can be used for secure logins in personal devices, access control in sensitive environments, continuous identity verification in healthcare, and variable devices that combine authentication with heart health monitoring. The advantages include high security due to liveness detection, adaptability to signal variation, and continuous real time verification capability. So, to conclude, our adaptive ECG biometric system shows how signal processing and biometrics can work together to build a secure, adaptive, and cost effective authentication platform. While our current work focuses on MATLAB simulation, it lays a strong foundation for future hardware implementation using sensors and microcontrollers. With growing importance in healthcare and security, ECG based authentication has the potential to redefine how identity and health data can be securely integrated in modern technology. Thank you.